In the previous section, we learned about scalar line integrals and vector line integrals. In section 6.3, we take what we learned, particularly about vector line integrals, and we learn how conservative vector fields are related to computing a vector line integral. We'll also learn how to determine whether or not a vector field is conservative, and if it is, how to find the potential function whose gradient gives us the vector field. We have several learning objectives in this section. We're going to start by describing some curves and regions. The curves are simple curves and closed curves. Then the regions are connected regions and simple regions. We can also combine these together so that we can have a simple closed curve or a simply connected region. When we're talking about a curve, we're talking about something that looks like a wire in either two-dimensional or three-dimensional space. When we're talking about a region, we're talking about a subset of either R2 or R3. In other words, a two or a three-dimensional region. Our next learning objective is to explain how to find the potential function if we know that a vector field is conservative. We'll also learn about the fundamental theorem for line integrals, and we'll use it to compute the vector line integral in a vector field. And finally, we'll also learn how to determine if a vector field is conservative. Let me share my screen, and we'll get started by first defining the different types of curves and regions we'll be working with in this section. In order to continue our study of conservative vector fields, we need to define some types of curves and regions that will feature largely in theorems in the subsequent chapters or sections of this chapter. When we're looking at these, we're going to start with the different kinds of curves. We're going to start with closed curves and simple curves. We've already talked about closed curves before. A closed curve has the same point as both its beginning and ending place. A simple curve is one that does not cross itself or intersect itself. A curve can be both closed, where it comes back around to where it started, and simple, where it does not cross over itself. Let's go ahead now and take a look at the formal definition of a closed curve. A closed curve is one where there exists some parameterization such that if t varies from A to B, R of A is equal to R of B. In other words, it ends up where it started. The curve on the left is oriented because it does have a direction, but the end point does not equal the beginning point. So this is not a closed curve. The curve on the right, however, forms a loop. Curves that form loops are by definition closed because wherever the t value starts, when you end, you'll end up right back at the same value. There may be other ways to parameterize the curve, but the definition of the closed curve just says there does exist one where the beginning and the ending point are the same. Now let's define what we mean by simple curves. A simple curve is simple if it doesn't cross itself. So in this case, there exists a parameterization R of t such that as t varies between A and B, R is 1 to 1 over that interval. In other words, there's no parameter value between A and B that returns the same value at two different locations. When we look at these curves that you see right here, the one on the far left is not closed, but it is simple. It never intersects itself. But because you don't end up where you started, it's not closed. The second one is both simple and closed. It does not intersect itself, and it forms a loop. The third one, which looks like a figure 8, is not simple because it intersects itself. There are two values for t that give the same value for the parameterization, R of t. where those values are not the same one, the t values. It is closed because it does form a loop. You do get back to where you started. The curve on the far right, which looks sort of like a 6, but with the curve continuing down, is not simple because it does intersect itself here. And it is also not closed because you don't end up back where you started. It is true that there is a loop in it, but the entire curve is not, in fact, a loop. So it is not closed. Let's take a look at the parameterization in example 1. We have the parameterization 2 cosine t, 3 sine of t, which we know is parameterization for an ellipse. In this case, it moves out 2 to the left and 2 to the right in the horizontal direction, and 3 up and 3 down in the vertical direction. This means that we have an ellipse with a major axis of 6 and a minor axis of 4. When we look at it, notice that t actually loops around this ellipse 2 times. When we're looking at it, when we go from 0 to 6 pi, 0 to pi will take us around 1 time, and then we loop around again a second time. However, when we think about, is the path itself simple? The answer is yes. There's no intersection where you have different t values giving you the same one. Is it closed? Yes, it is, because you both start and end at the point 2, 0. Let's now move on to define some regions. Before we move on, I want to cover one last item about example 1. Some of you may be confused because as you trace from 0 to 6 pi, you do hit all the values on the curve twice. And that means that r is not 1-to-1 over that interval. However, the definition of a closed curve is that there exists a parameterization where that doesn't happen, where it is 1-to-1. All we need to do to get that parameterization is to change the interval for t from 0 to 2 pi. And once we go from 0 to 2 pi, then we know that we'll only trace it 1 time, but we'll produce the same curve instead of tracing it, well, I guess it would be 6 times if we go around 3 times if we go from 0 to 6 pi. So the fact that this parameterization isn't 1-to-1 does not mean that there doesn't exist one that produces the same curve that is 1-to-1. And there is a parameterization. It's the same parameterization, but with t limited to 0 to 2 pi. Now let's define our regions. We want to start with the idea of a connected region. When we talk about a connected region, we want to take one where, given 2 points, distinct points in the region, there must exist a path that connects you from point A to point B, and it stays completely inside of the region. So let's take a view of a region here. Let's call this region D. And let's suppose I have 2 points in it. To be a connected region, I have to be able to get from point 1 to point 2 without leaving D. And that makes it a connected region. So what's not connected? Well, you can think about the continental United States and Hawaii as a not connected region. We can't walk from the continental United States over to Hawaii. So that part is not connected. Are we connected to Alaska? Yes, even though Canada is between us and Alaska, we can walk from here to there. Now, if we considered that our domain was just the United States, then we would not be connected to Alaska because we would have to leave the United States to get to Alaska. If we take the domain as North America, however, then we would be connected to Alaska. It depends on how you're defining your region. Let's now talk about a simply connected region. We'll have to make the definitions in both 2 dimensions and 3 dimensions because it means something slightly different in the different dimensions. We'll start with a simply connected region in 2 dimensions. It's a connected region that has no holes in it. And by holes, we do literally mean a hole. So if I have this, and inside of it, I have a hole, then that would not be simply connected. It's connected, but it's not simply connected. The reason it's connected is I can still get from a point here to a point here by going around the hole. But it's not simply connected because I can't take a shoestring, and I've got a shoestring right here. I can't take a shoestring and wrap it around no matter where I put the shoestring inside of D and cinch it to a point without going through that hole. And that means it's not simply connected. For 2 dimensions, the rule is simply connected regions do not contain holes. All right? And the idea, again, is that you're creating a loop of any type that stays in D, and you've got to be able to pull the loop down until it goes to a single point without leaving D. And the problem is, if I put the hole inside the loop, but I stay in D, when I start pulling on the loop and making it smaller and smaller, at some point, it exits D through the hole. All simply connected regions are connected, but not all connected 2D regions are simply connected. So if it's simply connected, it's connected, but just because it's connected doesn't mean it's simple. This region here is connected, but it is not simple, so it is not simply connected. Let's take a look at some images and determine whether or not we think they are simple and or connected. If we look at the trapezoid shape, it is a simple shape and it's a connected shape. I can put a loop anywhere inside of this, and no matter where I put the loop, when I tighten the loop and make it smaller and smaller, I'm staying inside of the trapezoid. The same is true of this, well, bumpy circular shape. And the same is true of this hexagon. However, when we look at the next region, notice that they are still connected. I can get from point A inside of the trapezoid with a hole to point B without leaving the orange space, but it's not simple. If I put a loop inside of this region around the hole and I tighten that loop, at some point it's going to pass through the hole, leaving the region. That means that this is connected, but not simple. The same is true of the 2 shapes to its right. So the top row, each region by itself is both simple and connected, or what we call simply connected. The next row, where there appear to be orange, are connected, but not simple because they have holes inside of the region. Let's look at the region on the bottom. Notice that they're both labeled D1. That means that D is the combination of these 2. Let's say Colorado and Hawaii. They're both in the United States. However, they're not connected. So in this case, when we're looking at it, it is not a connected region. Let's go ahead now and move on to the next possibility. A simply connected region in 3 dimensions. What does it mean for a shape to be simply connected in 3 dimensions? In 3 dimensions, it does again have to do with holes. You've got to be able to get from point A to point B inside the region without leaving the region. That's still connected. But this time, when we throw our loop around some part inside the domain, I can move it above, below, to the left, or to the right, or at an angle to avoid any hole that's completely encapsulated in the interior of that region. I would have a hard time, however, if it's a paper towel roll. Let's take a look at a paper towel roll. If you look at a paper towel roll, we can call this a region, and notice that it would not include the hole that goes through the center of the paper towel roll. The problem here is, while I can get from one point on the roll to any other point on the roll without leaving the roll, I cannot put a loop around it and tighten the loop tighter and tighter and tighter without eventually leaving the region. And the reason is, sooner or later, that loop is going to hit this hollow interior. This hole passes all the way through from one edge of the region to the other edge of the region. And that means that this particular region is not simple. So it is not simply connected. Again, all simply connected regions are connected, but not all connected regions are simply connected. Let's take a look at more regions. We have both two-dimensional and three-dimensional regions. We want to determine, are they connected and are they simply connected? Let's take a look at the first one that we see here. The first one is a circle with a hole in the center of it. Because it has a hole in the center of it, then we know that it cannot be simple. So is it connected? Take any 2 points in the blue shaded region. Can you move from that point to another point in the blue shaded region without touching the white? The answer is yes, you can. So this region is connected, but not simple. Let's go ahead and make note of that now. What about the region next to it? The region next to it looks sort of like a boomerang. It's a two-dimensional shape. Is it simple? Is it connected? Again, can you go from any point in the dark blue to any other point in the dark blue without leaving the dark blue? The answer is yes. That means it's connected. Is it simple? It's a two-dimensional shape, and the only thing that prevents a two-dimensional shape from being simple is a hole through it. But there is no hole. Yes, it kind of turns, but there's no hole surrounded by points within that region. So this one is both simple and connected, or what we would term simply connected. We have one more region that's a two-dimensional region in row 1. In this particular one, can we get from any point in the dark blue to any other point in dark blue without leaving the dark blue? The answer is yes, we can. We simply have to go around the hole sometimes. But we can do that and stay in the dark blue. So it is connected, but it's not simple, because to be simple, you have to be able to put a loop anywhere in the dark blue and cinch it down to a smaller and smaller loop without ever touching white. And that can't be done. If I put the loop around the hole, which will be entirely in blue, when I tighten it, it leaves the region. So our last one is again connected, but not simple. The second row, we have three-dimensional objects. The one on the far left is more or less like a basketball. So when we're looking at this one, everything within the sphere is dark blue. So is it connected? Well, yes, the entire interior is dark blue, so I can get from any dark blue spot inside the ball to any other. That means that it must be connected. Is it simple? For a three-dimensional region, what we're looking for is a hole that goes all the way through from one edge to the other, so that you could fly through the hole and never touch your region. In that case, it would not be simple. However, there's no hole that tunnels all the way through this three-dimensional basketball. That makes this three-dimensional basketball simple and connected, or simply connected. Let's look at the one next to it. The one next to it is like a hollow basketball, maybe more like, well, I suppose a tennis ball or something like that, where the interior is hollow, or maybe a Whopper, right? Those malted chocolate candies. They have a solid shell on the outside, but the interior is hollow. Is that simple? Is it connected? If you take it and you go from any point along the crust of that malted milk ball, can you get to any other part of the crust? And the answer is yes, you can. You can stay within the crust and go from any point to any other point. Is it simple? If you take a loop and you put it anywhere in the three-dimensional object, can you move this in such a way that you stay within the shape, but you don't enter the hole? And the answer is yes, I just have to move it a little bit so it's no longer around the hole and I can cinch it down. It's not possible to pass from one side of this three-dimensional shape to the other by passing through a hole, like a wormhole, without ever touching the blue region. I can't get from one side to the other without going through blue. That means that this hollow interior is completely encapsulated, which means that it is both simple and connected. We would call this one simply connected. The next one that we see here is again a basketball shape, but this time it's got a hollow tube going all the way through from one side to the other. I can't think of a shape that really has this sort of behavior, but it's sort of like you took a sphere and you tunneled a cylinder through the center of it. If you fly in the cylinder and stay within the interior of the cylinder, you can exit that sphere on the other side without ever touching the sphere. You can get from one side to the other without touching it, then it must not be simple. In other words, if I put a loop in here such that the loop passed around that interior but stayed only in the blue, no matter whether I move it up or down, when I tighten the loop, eventually, because this hole goes all the way through, eventually I have to touch the hole, and that makes it not simple. Is it connected? Yes, it is connected. I can move around by going this direction or this direction, or around without passing through the hole. So I can get from one point to another by staying within the dark blue, but I cannot cinch down the loop to a point without crossing through that tunnel. That makes this one connected, but not simple. What about the next one? Well, the next one basically is our toilet paper. It could be toilet paper or paper towel roll. It's the same. It's just a cylinder with a hollow tube through the center of it. And because that hollow tube goes all the way through, it is connected, but it is not simple. Let's now move on to talking about the fundamental theorem for line integrals. Anything called the fundamental theorem is probably something you should know. This one could be named the fundamental theorem for vector line integrals, because that's essentially what this is. It does not refer to scalar line integrals. It refers to vector line integrals. Most of our work in multivariable calculus is with vector line integrals. So we often drop the vector part of vector line integral, but you should be able to tell from the situation based on whether or not your function inside the integrand is a vector valued function. Let's remember what a conservative vector field is. Remember, we said that a conservative vector field is another name for a gradient vector field. In other words, there exists some scalar valued function f of x and y, or of x, y, and z, such that the gradient of f, del f, is equal to the vector field. In other words, we take the partial derivatives of our scalar valued function, and the partial with respect to x becomes the first component, the partial with respect to y becomes the second component, and if it's in 3 dimensions, the partial with respect to z becomes the third component. Remember, this is what we mean by the gradient of f. So when we write this down, the gradient of f is itself a vector representing the partial derivatives of the scalar valued function f. This would be the gradient in a 3-dimensional system. This becomes a vector field or a gradient vector field, and we call it conservative because it refers to physical systems in which energy is conserved. It could be a situation with some kind of charge, electrical charge, or it could be having to do with gravity. It is a relatively high bar to meet. Most vector fields are not conservative, but many of the situations that we study in physics and engineering have to do with electrical currents and with gravity. And those two situations are conservative vector fields. So while conservative vector fields themselves aren't common, we do commonly study them. So we're going to spend quite a bit of time talking about conservative vector fields. Let's go ahead now and think of this then in a way that f is an antiderivative of the vector field. If we think of del as a derivative operation, we took the derivative of f, and so f is sort of an antiderivative of the vector field. If we were to integrate both sides, we should get the potential function back. And we'll discover later at the end of this chapter or this section that that's exactly what we do to find the potential function of a conservative vector field. Let's look at the fundamental theorem for line integrals. We're going to start with a piecewise smooth curve. Remember, smooth means the first derivative is continuous and not the zero vector. And it has parameterization R of t for t varying between a and b. We'll let f be a function of either 2 or 3 variables, so 2-dimensional or 3-dimensional, with first order partial derivatives that exist and are continuous on C. All right, now that they're continuous on C, then we'll say that the vector line integral over the curve C of del f dot the dr vector differential is equal to the potential function, which is a scalar valued function, evaluated at r of b minus the potential function evaluated at r of a. This looks a lot like the fundamental theorem of calculus part 2 that refers to definite integrals. You evaluate the antiderivative at the upper limit of integration and subtract the antiderivative function evaluated at the lower limit of integration. So in a sense, what this is saying is we don't even have to know what the gradient of f is. We wouldn't even necessarily have to know what the vector field is. We simply need to know the parameterization, R of t, the limits on t from a to b, and what the potential function is. And we can compute the vector line integral from that. But this does assume, of course, that the vector field is a gradient vector field. In other words, it is conservative. Let's take a look at the proof. We're going to assume that we're in 3 dimensions, but the proof will actually apply to any dimension. Let's suppose that we are asked to compute the vector line integral of del f dot dr, the vector differential. From what we've learned about vector line integrals in section 6.2, we know that this means that we can compute the dot product of del of f of r of t dotted with r prime of t dt, given that the vector differential dr is equal to r prime of t dt. If we think about it then, what is del of f actually computing? Well, it's the partial of f with respect to x, the partial of f with respect to y, and the partial of f with respect to z. That's what del of f is. When we dot it with r prime of t dt, r prime gives us dx dt, dy dt, and dz dt. And when we take their dot product, we get del of f, or rather the partial of f with respect to x, times the derivative of x with respect to t, plus the partial of f with respect to y, times the derivative of y with respect to t, and plus the partial of f with respect to z, times the derivative of z with respect to t. Again, we're making use of the fact that this vector is the partial with respect to x, partial with respect to y, partial with respect to z. And this vector is equal to dx dt, dy dt, and dz dt. Once we have this, we can use the chain rule that we used earlier in this semester in order to simplify. Using the chain rule, what this actually then ends up telling us is that we're taking the derivative with respect to t of f of r of t, and the differential remains dt. Again, this is using the chain rule on this applied right here, which is going to give us that partial of f with respect to t. Since the last integral is just a single integral, a function of a single variable, t, we can apply the fundamental theorem of calculus, part 2, which tells us that we can find a definite integral by evaluating at the upper limit of integration and then subtracting the antiderivative evaluated at the lower limit of integration. This gives us the following formula, which is our fundamental theorem for line integrals, or the fundamental theorem for vector line integrals. And QED just indicates that we're finished with the proof. In other words, all we need are the initial and final points on the curve. We need to know where it ends up, and we need the potential function. We don't have to know anything about the vector field itself. Let's now talk about something else, something called path independence. What we've just discovered is that we have a type of line integral for which we know that changing the path will not change the value of the vector line integral. In the fundamental theorem, notice that this definition up here applies as long as the beginning and ending place puts us in the same location. It's not dependent on the path. It's only dependent on where you start and where you end up. We could say that in a sense, the valuation of this vector line integral is independent of the path or independent of the parameterization. Let's now take a look at what path independence is formally. Let's suppose we have a vector field F with domain D. We say that the vector field F is independent of path or path independent if when we evaluate F dot dr, the vector differential, on two different paths, C1 and C2, we get the same result. All right, now C1 and C2 have to have the same initial and terminal points. They have to begin in the same location and end in the same location. But they can take two completely different paths to get there. So they could start here and end here. One of them might maybe follow a path that does this. And the second one could follow a path that does that. What the fundamental theorem tells us is that gradient vector fields are independent of path. And if we have a vector field and we don't know whether or not it's a gradient field or conservative, but we do know that it's path independent, this tells us something more about it. Let's go ahead and summarize what we've learned so far. There are quite a few facts about conservative vector fields, and it can be confusing to put them all together. So I've listed them all on one page, and we're going to combine different ones to get new summary statements. We're going to start with the one that we just looked at, which is that del of f dot dr, the vector differential, is independent of the path. In other words, by the fundamental theorem of line integrals, we only need to know where it started and where it stopped. As long as those point to the same, it doesn't matter what path we take to get there for a conservative or gradient vector field. The next one says if F is a conservative vector field, then it must be independent of path. Well, this is basically saying the same thing as item number 1 does, because del of F is, of course, a gradient vector field, which is conservative. So the first two are really saying the same thing, just in slightly different ways. Let's look at the third one. The third one is probably the most complicated of all the ones we have to look at. It says start with a continuous vector field on an open connected region. So my region is connected and my vector field is continuous, meaning that the functions that make up the vector field are continuous functions. If I have a continuous vector field on an open connected region, 3 conditions, and at a 4th condition, it is independent of path for any path, then it must be conservative. Being path independent alone is not enough to guarantee that it's a conservative vector field. But if we add that it is a continuous vector field on an open connected domain and it's path independent, those 4 things together prove that it is a conservative vector field, which means there is a potential function, lowercase f, such that del of f dot dr is, of course, independent. Let's take a look at the next few. Number 4 states that if a vector field f dot dr, the vector differential, is independent of path, then if the path is closed, f dot dr has to equal 0. Well, this should make sense if we think about what we have in the fundamental theorem for line integrals. We know that this applies to conservative vector fields. So if it's a conservative vector field, we can apply this. And what it's saying is that if it's a closed loop, then R of A and R of B are equal to each other. You're ending up back where you started, definition of a closed loop. In that case, then f of R of A and f of R of B will be exactly the same value, so subtracting them should give you 0. And that's exactly what we're stating in item number 4. Note that item number 4 does not imply that it has to be a conservative field. It simply says if it's independent of path, then f dot dr will give me 0 for every closed path. Item 5 reverses the sense of item 4. We switch the if and then parts. This is called the converse. When we're looking at item 5, it says if f dot dr equals 0 for every closed path, then it must be path independent. But remember, path independence does not bias conservative. To get conservative, we need path independence plus continuous, open, connected domain. We need 4 things. From the previous 2 items, from 4 and 5, we can rewrite 4 and 5 in one statement that says f dot dr is path independent if and only if f dot dr equals 0 for every closed path. But again, this does not prove it's conservative. Then we're going to combine 2 and 4. If we combine 2 and 4, if it's a conservative vector field, then what do we know? Well, 2 told us it's path independent. But the combination of 4 and 5 tells us if it's path independent, then f dot dr equals 0 for any closed path. So then we know that for a conservative vector field, f dot dr will be 0 if it's forming a closed curve. If we combine the last 2, 6 and 7, then we can get the final statement down at the bottom. A continuous vector field on an open connected region will be conservative, I've got 3, if and only if it's path independent. On this particular problem, you're assuming continuous, open, and connected. Then you get conservative if and only if you have path independence. But if you have path independence and you have continuity, open, and connected, then it must be conservative. Fact 7 should make a little bit of sense to you if you think about a particle in a gravitational field, or maybe just think about yourself when you're hiking. If you start on any path and you hike around the mountain, but you come right back to your base camp, then the work done by gravity on you is 0. If you leave the next day and you take a totally different hike and go in totally different directions, but you come right back to the same point, again, the work done by gravity is 0. You end up where you started. Let's now take a look at example 3. In example 3, we're given that the function f of x and y equal to x minus 1 quantity squared y plus quantity y plus 1 squared times x is a potential function for a vector field. The vector field is given by 2xy minus 2y plus y plus 1 quantity squared for the first component, and x minus 1 squared plus 2yx plus 2x for the second component. We want to calculate the vector line integral f dot dr, where dr is the vector differential, where c is the lower half of the unit circle oriented counterclockwise. Now, we do, of course, have the option of computing f of r of t dot r prime of t dt. However, since we're told that it is, in fact, a conservative vector field, and we're given the potential function, we can use the fundamental theorem for vector line integrals to cut right to the chase and simply plug in at the beginning and ending point on our curve. So again, you do have the option of computing f dot dr by first writing the parameterization and integrating from t equal a to t equal b of f of r of t dotted with r prime of t dt. It is an option, but as we'll see at the end of this section, sometimes that can be an enormously difficult integral to evaluate. And using instead the fundamental theorem for line integrals is much shorter. In this case, it will in fact be much shorter. What we need to determine is what's the beginning and ending place and what is the parameterization of this curve. We're told it's the lower half of the unit circle, so radius is 1, oriented counterclockwise. So if we look at this vector field and we look at an image of it, if we go counterclockwise, then we're talking about orienting from this direction to this direction. So we're going to start here at -1, 0, and we're going to end here at 1, 0. So I need a parameterization that will do this, and I need to know what the value of t is that puts me at the starting point, -1, 0, and what value of t puts me at the ending point at 1, 0. Go ahead and pause the video to write out the parameterization only, then turn the video back on and we'll discuss it further. In order to parameterize a circle, we take the radius of the circle and we let x be the radius times cosine of t and y be the radius times sine of t. Since we're using a unit circle, the radius is 1. So our parameterization is cosine t sine t. To get it to start over here in the image at -1, 0, what we want to do is to start at pi and travel to 2 pi. Or similarly, you could travel from -pi to pi. This will give you the same values. Once you have found the parameterization, you can use the fundamental theorem for vector line integrals, and you can compute what r evaluated at the end point for the interval for t, b, is, and compute what r of a is. In other words, I want to evaluate r when t is pi for r of a, and when t is 2 pi for r of b. Go ahead and pause the video to work that out, then turn the video back on, and we'll continue with this line integral. Okay, looking at it, we want to evaluate r of a and r of b, where r of a is given by r of pi and r of b is given by r of 2 pi. When we do this, for r of pi, we get cosine pi sine pi, which gives us the value of the vector as -1, 0. When we evaluate at 2 pi, we get cosine 2 pi sine 2 pi, which gives us the vector 1, 0. These become the vector values that we substitute into the potential function f in place of x and y. So to find f of r of a, I'll replace x with -1 and y with 0. To find f of r of b, I'll replace x with 1 and y with 0. Remember that the fundamental theorem of line integrals tells us that we can go straight to the end and compute f of r of b minus f of r of a. Let's go ahead and look at what this gives us. If I compute f of r of b, I'm taking f of 1, 0. When I multiply this into my definition for f, which is x minus 1 quantity squared y plus y plus 1 quantity squared x, I get the value of 1. When I substitute r of a into f, I get the value of -1. And 1 minus a -1 gives me 2. The value of the vector line integral is 2. I could also have found this, of course, by computing the vector field with r of t substituted inside dotting it with r prime of t and integrating with respect to t from a to b. That, however, would probably be a longer and more difficult process because the expression for f is quite complicated, as you can see up here. Notice that in order to find the value of this vector line integral, we never actually used the definition of the vector field uppercase letter F. Let's take a look now at example 4. In example 4, we want to show that a vector field given by xy, comma x squared y squared is not path independent by considering the line segment from 0, 0 to 2, 2, and the piece of the graph y equals x squared divided by 2 that also goes from 0, 0 to 2, 2. Remember that path independence alone is not enough to tell us it's conservative. To tell us it's conservative, we need a continuous vector field on an open, connected domain that is also path independent. However, if we take away path independence, then it cannot be conservative. So proving it's not path independent is a way of proving that it's not a conservative vector field. You can't possibly prove that a vector field is path independent because, like what we happened when we were doing limits, you can't test all possible paths. What you can prove is that it's not path independent by showing that you get two different values for your integral depending on the path that you take. Let's take a look now at what our two paths are. When we look at the two paths, we've got curve 1, which will let be the line segment from 0, 0 to 2, 2. This is pictured here in red with arrows pointing from the origin to the point 2, 2. The second path we're going to consider is 1/2 x squared, which also proceeds from the origin out to the point 2, 2. In order to decide whether or not it's path independent, the first thing we want to compute is simply the vector line integral. This will let us determine whether or not it's even possible for that vector field to be conservative. In this case, we're going to start by parameterizing the line segment. There are various ways of parameterizing line segments. We've learned at least 3 or 4 methods thus far. Go ahead and parameterize the line segment and then compute f of r of 1 and find r prime of t, and then turn the video back on, and we'll compare our results before proceeding to the next step. So in this case, there are various ways of parameterizing. Of course, there's infinitely many, but one simple way is to let x be 2t and y be 2t, and that will vary t between 0 and 1. You could also have chosen to let x be t and y equal 2t, since that's the equation of, or rather y equal t, since that's the equation of the line y equal x. And that's basically what we have. That, however, would vary the parameter from 0 to 2. Both will work. Both are equally as good. There's not any advantage to one over the other. I chose to use 2t, 2t, t between 0 and 1. It makes my limits of integration simpler, but it makes my functions a little bit more complicated with a constant. Now I need to find the vector field composed with the parameterization f of r of t. Since f is xy for the first component, I multiply 2t by 2t to get 4t squared. Since the second component of f is x squared y squared, I square 2t, square 2t, multiply them together to get 16t to the 4th. Finally, in order to compute the vector line integral, I need to find r prime of t. In order to compute r prime, I simply take the derivative with respect to t, which gives me 2, 2. My next step is to find the dot product between f of r of t and r prime of t, and then to evaluate the single integral from t equal to a, which is 0, to t equal b, which is 1. Pause the video to complete this step, then turn it back on and we'll proceed to the next curve over which we want to evaluate the vector line integral. Once we've found f of r of t and r prime of t, we need to dot them together to form the integrand of the integral. This gives me 4t squared times 2, or 8t squared, plus 16t to the fourth times 2, or 32t to the fourth. Then we integrate from the parameter value t equal a to t equal b, which for me was from 0 to 1. When I integrate, I get 8/3 t cubed plus 32/5 t to the fifth, evaluated between 0 and 1, which gives me 8/3 plus 32/5, which is going to give me 136 divided by 15. This is the value of the vector line integral along the path going directly from the origin to 2, 2 along the line y equal x. Now we want to repeat the process, but we want to do it on a different path. Again, we're trying to show it's not path independent, which will mean, of course, that it cannot be conservative. This time we want to start and we want to use the equation y equals 1/2 x squared. We need to go ahead and parameterize this, and then we will be able to find f of r of t, r prime of t, the dot product, and the integral. Go ahead and pause the video to work out all of this second part, and then turn the video back on, and we'll compare our results with what we got along the first path. Let's take a look at integrating the vector line integral f dot dr along the second path, pictured in blue here, along the path y equal 1/2 x squared, again from 0, 0 to 2, 2. In this case, we can parameterize the curve by letting x be t and y be 1/2 t squared. Since x goes from 0 to 2, then t goes from 0 to 2. Then we can substitute in this parameterization into our vector field. And when we do this, we get f of r of t will be xy for the first component. So t times 1/2 t squared gives us 1/2 t cubed. And the second component of f, x squared y squared, gives us t squared times the quantity 1/2 t squared all squared, which gives us 1/4 t to the sixth. In order to compute the vector line integral, we need f of r of t dotted with r prime of t, so we need to find r prime. Based on my definition of r as t 1/2 of t squared, r prime becomes 1, t. Then I take the dot product of f of r of t with r prime of t, and I get 1/2 t cubed plus 1/4 t to the seventh. This is simple to integrate from t equal to a at 0 to b at 2, and this gives us 1/8 t to the fourth plus 1/32 t to the eighth. When we evaluate between 0 and 2 and simplify, we get the value of 10. However, 10 is not equivalent to 136/15, which was the value of the vector line integral that we found using a different path. This means that this vector field is not path independent. And if it is not path independent, then it cannot be a conservative vector field. This section is rather long, so I'm splitting the video into two parts. And the second part, we'll be taking a look at the two remaining questions about vector fields. Namely, how do we know if a vector field is conservative? And if we do know it's conservative, how do we find that potential function, lowercase letter f, so that we can use the fundamental theorem for line integrals to evaluate the vector line integral f dot dr. See you soon for the next video.